Hello class, welcome to Unit 4, Video 6. Today we're going to go ahead and look at complex numbers. The learning targets for today are that you can find square roots and perform operations with pure imaginary numbers. You will also be able to perform operations with complex numbers. Alright, so some rules we need to go over first. Product and quotient properties of square roots. The first one is the product property. So if I'm multiplying a times b, I can break it into square root of a times the square root of b. An example of this is if I have the square root of 16. Okay, we all know the square root of 16 is 4. But I could think about it this way. The square root of 16 I can write as 4 times 4. And then I can go ahead and break it apart. What is the square root of 4 times the square root of 4? We know the square root of 4 is 2. So I would have 2 times 2, which gives you your answer of 4. So that's how the product property works. Another way to think about it, if I have square root of 81, once again we know the square root of 81 is 9. So this is 9 times 9, okay? And whenever something is doubled up, kind of like it is here, what I want you to notice is if it's paired up and this is the square root, okay, so you can think about it as having a little 2 here. Since it's a square root and there's a 2 there, if they're paired up, you can write it out in front. So this one I would really have just 9. And here is my written out reason why. This radical really means the square root, or the little 2 here, of 81. Okay, and since there is a pair of 9s, I can write it out in front. Or sorry, write it outside of the radical. We're also going to look at cubed roots. So one thing to notice about a cube root is guess how many you'd have to have underneath. You'd have to have a group of 3. So if I have 3 times 3 times 3, okay, there's 3 of them. It's a cubed root, so my answer for this one would be 3. Something to keep in mind. The next rule we're going to look at is the quotient rule. So that's when we have division. So you can go ahead and break that one up as the square root of a over the square root of b. So one example is if I have, you can write it over here on your note sheet if you have room, square root of 49 over 64. Okay, I can break it down, square root of 49 over square root of 64. Square root of 49 is 7, square root of 64 is 8, so my answer would be 7 over 8. One reminder is that simplified square roots do not have radicals in the denominator, and any number remaining under the square root has no perfect square factor other than 1. So if I say to simplify something, that means that you do not have a radical written in the denominator. Okay, so just a reminder, if I have a fraction, the top is the numerator, the bottom is the denominator. Okay, so you wouldn't leave this radical in the denominator. You'd have to rationalize the denominator. Also, you'd have to simplify anything underneath the square root. Okay, so there's no perfect square other than 1. Okay, so we'll look at some things like that as we go through the examples. Something that's going to help us on the problem today is knowing the perfect squares. So if you would like to, you could pull up Google perfect squares chart, and you'll get all the perfect squares, because 2 times 2 is 4. 3 times 3 is 9. The other way to think about it is if I'm given this number, so let's go with 121, so a square root of 121, well, that is just 11. Okay, so it's the opposite way. So you can either multiply to get to the numbers or go reverse. All right, so moving on. First example, we are going to be breaking down radicals into simplest form. And it's essential when you are going to use the quadratic formula to solve quadratic equations. So the reason we're doing this now, is because we're moving on to the quadratic formula next. Okay, so after this, we're doing quadratic formula. So we need to simplify the square roots. I have went ahead and put some of the perfect squares on here for us. So some to remember. So looking at A, it's a square root of 50. I would say, what's my perfect square in 50? Okay, so I look through my perfect squares, and the easiest one to see is 25. 25 times what gives you 50? Well, 25 times 2 gives you 50. So then I can break it apart. It's really square root of 25 times square root of 2. Square root of 25 is 5. Square root of 2 is not a perfect square, so we leave it like this. Okay, this is one approach. Your second approach is you could make your factor tree for 50. I would say 2 times 25, and I know this breaks down into 5 times 5. So underneath my radical, I would have 2 times 5 times 5. And as I talked about before, this is really a square root. So if there's a pair, I can write it out in front, and I will get the same answer. So whichever method you will feel most comfortable with, I would use that one. Okay. Square root of 45. I can see that one right away. 9 times 5. Breaking it apart, it's square root of 9 times square root of 5. Square root of 9 is 3. Square root of 5 is not a perfect square, so my answer is 3 square root of 5. Moving on to C. We have the square root of 128. Okay, this is a bit bigger number, so I'm just going to start and divide it by 2 and see what happens. If I want on my calculator, I would say 128 divided by 2. That's going to give me 64. So it's 64 times 2. And I would notice 64 is a perfect square. What's the square root of 64? It is 8. So I can break it apart. So I have 8 square root of 2. Okay. Is there other perfect squares in 128? Yes, there are. Some people might notice, okay, so this is another way to do it, is that it's 16 times 8 is 128. So I could break this apart. Square root of 16 times square root of 8. And I know the square root of 16 is 4. The biggest thing you need to remember is square root of 8. Can I break that down any further? Yeah, it's 4 times 2. The square root of 4 is 2. So I'd still have square root of 2 underneath. And then I would have 4 times 2, so 8 square root of 2. Did I get the same answer? Yes, just 2 different ways of thinking about it. Okay. Moving on to D. We have x squared. Okay. There's a few ways to think about this. The first way we're going to think about it is x squared. I can really think about it as x times x. So since it is paired up, I can go ahead and write it outside the radical. So my answer would just be x. The other way to think about it is a radical, okay, especially if there's a 2 here. This is, if I have the square root of x, it's really x to the 1/2 power. Okay. Well, if I rewrite this one as x squared, since it's the square root to the 1/2 power, I would have 2 times 1/2, which leaves me x to the first, which gives me my answer of x. Biggest thing to remember is that if it's a square root and it makes a pair of 2, so if I have a 2, a 4, a 6, a 8, I can write it out in front. Okay. So the next one is a good example of that. We have the square root of 25, x squared, y to the 4th. So let's just break it apart into each thing. So I have square root of 25 times square root of x to the 2nd times square root of y to the 4th. Okay? Well, the square root of 25 is 5. We just did the square root of x squared. The other way to think about it, though, is if I have a 2 here, it's really to the 1/2 power. So 2 divided by 2 gives you 1. So I have x to the 1st. Here, once again, it's really a 2. So it's really 4 divided by 2, which gives me, it's a y squared. So my answer I would write as 5xy squared. And there is my final answer for that one. Moving on to F. Let's go ahead and break this one down. I have square root of x squared over the square root of x. Here, my radical and my 2 will cancel. Same logic as up here. So I have x over square root of x. I said if you are going to simplify something all the way, you cannot leave a radical in the denominator. So what we do is you multiply what will give you the pair. So right now I have an x, so it'd be nice if I had another x. So I would multiply by another square root of x. Okay, this process that we're doing now is called rationalizing the denominator. And there's supposed to be g at the end, the denominator, the bottom. Okay, rationalizing the denominator. So I simplify this. I would have x square root of x over, Okay, well, just like we did before, I can put these together and write them as one. It's really square root of x times x. I have a pair, so I can write them out in front. So I have x square root of x over x. And I would look and see if I could simplify this any further. X over x will cancel, and so my final answer is just the square root of x. Okay, so there's a lot of things going on question F, but if you have questions, please be sure to ask. Okay, moving on to example G. Okay, we're going to break it apart. So it's a quotient rule. It's being divided, so I have square root 11 over square root of 49. Square root 11, not a perfect square, so I leave it as square root 11, and square root of 49 is 7. I would say to myself, is there any perfect squares in here? No, 11 is just 11 times 1, so this is my final answer for G. H. We have square root of 32, really over the square root of 81. So square root of 32 is not a perfect square, but I would think to myself, is there a perfect square in 32? 16 times 2 is 32. All over square root of 81 is 9. So I have square root of 16 times square root of 2 over 9. Well, square root of 16 is 4. Square root of 2 over 9. And I would say 4 over 9, can that simplify? No, it cannot. So this is my final answer. All right, one last one until we move on to something else. Break it apart, square root of 32x all over square root of 8. Square root of 32 we just broke down. Okay, we just broke it down. It was 16 times 2, but we have an x this time, so times x. All over, square root of 8 is not a perfect square, but my perfect square in there is 4, so 4 times square root of 2. Now let's go ahead and just write everything out. So I have square root of 16, which we know is 4. Square root of 2, can't do, and square root of x. All over, square root of 4 is 2, and square root of 2 we do not have. We do not have a perfect answer for that one. And if you notice, my square roots of 2, exactly the same, they will cancel. And lastly, 4 divided by 2 is 2, and I still have 2 square root of x. So my final answer is 2 square root of x. Okay. We are going to go ahead and switch gears into the square root property. So if you have any questions on simplifying radicals, please write them down. Please come and ask. Otherwise, I'm going to move on to using square roots to solve for x. Okay. One thing I want you to notice, all the problems we're going to solve are quadratics, but they are missing a b term. So remember, quadratics are ax squared plus bx plus c, okay, equals 0. That's how you would solve them. The problems we're going to solve do not have that bx term. Okay, if they do not have a bx term, you can solve using the square root property. Okay, so this is another way to solve quadratic equations. So I look at A. I know there's an x squared and I know there's a number, but there's nothing with an x. So I can add 25 to both sides. I have x squared is equal to 25. And now, if I want to get x by itself, take the square root on both sides. Remember, when you take a square root, you get two answers, plus or minus. So those cancel, and I'm left with x is equal to plus or minus the square root of 25. Well, the square root of 25 is 5. That plus or minus means my answer is 5, or x is equal to negative 5. The reason that we have to include both answers is if I square something, positive or negative, it will come out positive. So for instance, 5 squared is 25. 25 minus 25 is 0, so that works. If I plug in negative 5 squared is negative 5 times negative 5, which gives you positive 25. 25 minus 25 is 0. So both my answers work. But remember, whenever you take the square root, two answers, positive and negative. Looking at B, okay, once again, I have a number and an x squared. There's nothing with just an x, so I can use the square root property. I'm going to add 45 to both sides, so I have 2x squared is equal to 53 plus 45 is 98. Got to get my x squared by itself first, so I would divide both sides by 2. So x squared, 98 divided by 2 is 49. take the square root, get my two answers. So x is equal to plus or minus the square root of 49. So x is equal to plus or minus 7. All right. Good. Moving on to C. Okay. This one does just have an x, but do you notice how there's a square around it first? Okay, so it's really like an x squared, and the way I'm going to handle it is I'm going to get this piece by itself. So to do that, I would add 12 to both sides. Okay, then I have x plus 2 squared is equal to 13 plus 12 is 25. Now, in order to get rid of a square, I would square root. Remember, plus or minus. So I have x plus 2 is equal to plus or minus the square root of 25, which is 5. Now, I'm going to have two different answers. So I would have x plus 2 is equal to 5, and I have x plus 2 is equal to negative 5. And I would solve each one. Minus 2 here. So my first answer is x is equal to 3. Minus 2 here, and I get x is equal to negative 7. If you want to check your answers, feel free to plug them back in and check them out. Okay. We have one more with the square root property, so let's go ahead and take a look at that. Once again, I have an x squared term and a number, no b. Okay, so I would subtract 48 first. So I have negative 48. Then I go ahead and divide by 3. So I have x squared is equal to negative 48 divided by 3 is negative 16. Okay. Moving on from here, I do the same process, take the square root. So I get x is equal to positive or negative square root of negative 16. All right, you guys have been told over and over again that you cannot take the square root of a negative. Okay, now times are going to change. You're going to hear different. The square root of negative 1 is what we call an imaginary number I. Okay, so we're going to start talking about imaginary numbers. So I can rewrite this one as an imaginary number. So x is equal to plus or minus the square root. I'm going to write it as negative 1 times 16. Taking a little further, I can write it as square root of negative 1 times square root of 16. So x is equal to plus or minus, what is the square root of negative 1? It's imaginary I. And the square root of 16 is 4. So I would have 4i. So my answer is an imaginary number. Which leads us into our next part of the notes. What is an imaginary number? An imaginary number was invented by René Descartes, and it was proposed that the number I can be defined such that I squared is equal to negative 1. Okay, I squared is equal to negative 1, and also if I take the square root on both sides, I is equal to square root of negative 1. So these are the two things you need to remember. You need to remember that I is equal to square root of negative 1, or I squared is equal to negative 1. And one way to see where that comes from, if I square both sides, so I squared equals negative 1. So these are the important things that you want to remember. So here's another example, okay? I can solve this one using the square root property because I have just a number and an x squared term. So I'm going to subtract 2. So I have 2x squared is equal to negative 2. I would divide both sides by 2. Now I have x squared is equal to negative 1. Then I go ahead and take the square root. So x is equal to, remember, two answers, plus or minus square root of negative 1. And the square root of negative 1 is I. So my answer for this would be x is equal to plus or minus I. Okay? So imaginary numbers are something new that we need to add into our set of numbers. Okay, so let's go ahead and relate imaginary numbers to what we've already known, or what we already know. Okay, so in the Venn diagram below, we want to place real numbers, rational, irrational, integers, whole numbers, natural, complex, and imaginary. Okay, so I am going to start with the most basic type of number. Okay, well, to be basic, you start natural. So that is your innermost circle here. Okay, so my natural numbers. Examples of natural, they're also called counting. So when you start counting, you count with 1, 2, 3, and on. All right, so there's natural. The next number I'm going to talk about, what comes after natural? Whole numbers. So these should all be types of numbers you have heard of before. So I have my whole numbers. Think about whole. So we have naturals inside of whole, and whole, remember, starts 0, 1, 2, 3, and you count up. I always remember whole starts with like 0, which looks like a whole. Okay, so that's one way to remember it. From our whole numbers, anybody remember what adds on my negatives? Those are the integers. Where are they on my list? Integers. So these are positive and negative numbers. So my integers are ... kept counting. So -2, -1, 0, 1, 2. Okay, it's hard on my screen, but try and write that integers part right in the circle here for integers. Okay, so it's my integers. After integers, okay, integers are a set of rational numbers. So here's rational. Biggest thing to remember about rational is they can be written as a ratio or a fraction. So one example would be 5/7, or any number that repeats. So 0.3 repeating, that can actually be written as a fraction. All right. Now, this should be all stuff that you know. And there's one more term that you should know. Okay, so we just took care of rational. You should also know real numbers. Okay, so our numbers, all of these numbers are real. Okay, so rational is that you can be written as a fraction. What is it that when you can't be written as a fraction? Irrational. So irrational is over here. That is also a real number. So this is irrational. Some examples of irrationals, famous one is pi. Any square root, so like square root of 2, any square root that's not a perfect square is irrational. Square root of 7, square root of 11, they're all irrational. And another one is e. We'll get to the number e when we get to exponential functions, but something to keep in mind. So this big circle, we have all heard of the words in here before. Okay, now we have to go ahead and add in complex and imaginary. Okay, imaginary numbers are over here. They do not touch my real numbers. Okay, so this is imaginary. Okay, imaginary numbers are things that include I. So 5i is one example. I could have -7i. Those are all imaginary. Then the last thing we need to add on here is what we call the complex numbers. Okay, all numbers are complex. Okay, so I'm gonna, the big box that includes everything are the complex numbers. The reason all numbers are complex are because they have a real part and an imaginary part. So an example of a complex number might be 2 plus 5i. Real part, imaginary part. Another example of a complex number maybe is -1 minus 7i. Okay, real part, imaginary part. So the set of numbers and what kind of numbers they contain is important to know. This will show up on the ACT. So if you have any questions on how the set of numbers works, please let me know. The smallest is natural. We get to and then whole, then integers, then rational. Okay, then all of those are real numbers, and there's two types of real: rational or irrational. And then our complex numbers are broken into two things: real or imaginary. Okay, so let's go ahead and do some work with some imaginary numbers. So simplify square roots of negative numbers. So it's going to be the same as what we have done, but now we're going to be including I. So for 3a, I would just start out as writing -1 times. Now let's think about 18. What's my perfect square in 18? 9. So 2 times 9. One thing that I like to do when I'm simplifying is if I can write it outside of the radical, I underline it. Because what is the square root of -1? I. Times, what is the square root of 9? 3. And the square root of 2 I can't do, so square root of 2. When we write this out, it's kind of like an x. We would write 3i square root of 2. And that would be my answer for 3a. Moving on to B, same type of idea. I would have negative 1 times 125. What's my perfect square in there? 25 times 5. Okay, now the next one is a little tricky. It's an x to the 5th. So what I really want to do is rewrite it so I have an even part. And by that I mean I'm going to write x to the 4th times x. Remember, when you multiply, you add exponents. So 4 plus 1 is 5. All right, so let's simplify. Square root of negative 1, I. Square root of 25, 5. Square root of 5, can't do, so underneath my radical. Square root of x to the 4th, so it's like a 2. So I would take 4 divided by 2, which gives me x squared. 1 is not evenly divisible by 2, so it stays underneath my radical. Here is my answer simplified. Okay. Moving on to example C. All right. Common mistake is that people say, well, negative 10 times negative 15 is going to be a positive 150 when you combine them. You need to be careful. This is imaginary. This is imaginary. So we need to take care of each part first, and then we can combine if needed. So I'm going to think of this as negative 1 times 10 times negative 1 times 15. I would say the square root of negative 1 is I times square root of 10. And the square root of this one is I square root of 15. Okay. To simplify further, I would have I times I, which is I squared. Then I have square root of 10 times 15, which is 150. I squared. Well, remember, I is equal to square root of negative 1. If I square it, I squared is equal to negative 1. So this is really negative 1. I would say to myself, what is my perfect square in 150? 25 times 6. So I would have negative 1 times square root of 25 is 5, square root of 6. So my final answer is negative 5 square root of 6. Okay, there'll be one like this on your homework, so just be careful about that. Got to take care of the imaginary part. Let's do D. So now we're not having radicals, we're just simplifying with imaginary. So I'm going to solve it the same way that I did before. I'm going to go ahead and say, what's 2i times 7i? Well, negative 2 times 7 is negative 14. I times I is I squared. We just said I squared was negative 1. So my answer is positive 14. So that is how we would do D. Okay. Now example 4, we're going to work on simplifying. So we're going to be adding, subtracting, and multiplying imaginary numbers. When you see adding it, you're really happy. All you need to do is combine your like terms. So 6 and 1 I can combine. That's 7. Negative 4i and 3i, well, negative 4 plus 3 is negative 1i. So 7 minus I. Okay. And once again, remember this is our complex number. The reason it is complex is because there's a real part and an imaginary part. If there was only an imaginary part, it'd be an imaginary number. If there was only a real part, it'd be a real number. Okay. B, a little different, we're subtracting. So my recommendation, distribute that negative. So negative times negative is plus 1. Negative times positive is minus 2i. Then we're going to combine like terms. Negative 2 plus 1 is negative 1. 5 minus 2 is a positive 3i. There is my answer for 4B. 4C, okay, this one is multiplying. Notice, okay, a lot of people just don't notice the operation in between. Multiplying, there's no addition sign, there's no subtraction, so we're multiplying. The way I do this one is I multiply or I FOIL. So I would have 36 plus 6i minus 6i minus I squared. Okay, combine like terms. These two will cancel, so Get rid of those. Then I have 36 minus, well, what is I squared? Negative 1. 36 minus a negative 1 is really plus, so I have 37. One thing I want to point out to you is that example C is what we call a conjugate. It says, what is a conjugate? Well, this is an example of a conjugate right here. Notice it's the exact same thing, but one has a minus, one has a plus. Here is another example of a conjugate. Conjugates are nice because sometimes you need to get rid of the imaginary part. And look it, I was only left with one number. So it's good to notice what a conjugate is, okay? It's the exact same thing. One's positive, one's negative. If I look at D, is that a conjugate? No, they're not the same. The conjugate, for instance, for 2 plus I, if I wanted to know the conjugate of that, it would be 2 minus I. Okay. So take note, this one is a conjugate. So let's go ahead and do D. Same thing, it's multiplying, so I'm going to FOIL. So this gives me 6 plus 3I plus 4I plus 2I squared. Combining like terms, I have 6 plus 7I plus 2I squared. Remember, that's negative 1. So I have 6 plus 7I, and then 2 times negative 1 is minus 2. Combine my like terms, I would have 4 plus 7I. That would be my final answer for D. All right, one last problem on this note sheet, okay? Example 5, the base of a parallelogram is, so base is, remember is means equal, so B equals half its height. How do you do half of a height? 1/2 times H. If the area of the parallelogram, so area is 118, what are the lengths of the base and the length of the height of the parallelogram? So you have to remember the equation for area of a parallelogram. Base times height. Okay? I know what B is, so I'm going to take this, plug it in for B. So my area is equal to 1/2 H times H. Okay? Well, and I'm going to mark in what my area is. My area is 18. So 18 is equal to 1/2. H times H is H squared. Now, I can solve this using the square root property because there's no H by itself. So first thing I'm going to do is multiply by 2 on both sides. 18 times 2 is 36, so I have 36 is equal to H squared. Then I would take the square root. The square root of 36 is 6, so positive or negative 6. The biggest thing here is we're talking about height, so can you have a negative 6? No. So the height is equal to 6. The way I figure out my base is I plug it back in. It's 1/2 times the height, which is 6. What's 1/2 of 6? 3. So my base is equal to 3, and we should always label inches. So my height is 6, and my base is 3. All right, that is the end of Unit 4, Video 6. Sorry it got a little long. If you have any questions, please write them down. Otherwise, have a great day.